Okay, let's take a look at the syllabus. Okay, so we are writing here. Let's see, we still have to do something else in chapters 5. And if we manage to finish it, we will start on chapter 6, UCM3. Okay, let's see how is the notes here now. Oh, let's not forget, exam, right, is the day after tomorrow. Okay, so it's scheduled for the day after tomorrow. If you need let's see, you're going to have a holiday on Monday. And now notice that we're kind of running out of time because the other exam is going to be what, 3 weeks afterward? 1, 2, yeah, 3 weeks afterwards, right? And then we're going to have 1, 2, 3 weeks, and then 3 weeks after for the final, right? So if you believe you need more time to prepare for the exam, I think we still can postpone it for the next week, but it's, it's up to you folks. Okay, we still have a chance to postpone the exam for next week, but if you prefer that, we can do it. Okay, we will have to postpone this one as well. But think about that. Okay, think about that on your side, and if necessary, we will postpone another week for this exam if you feel you're not prepared, right? So that's the message that I want to send you. Let's see here. This is the notes. Break. Insert. Page break. One more student showing up here. Today is October the 28th, 2024. That's a Monday. Paragraph. There you go. So messages here, right? 1, exam 2 is scheduled for the day after tomorrow, Wednesday. 2, there's still a chance. There's still a chance to postpone this exam if you feel you're not prepared. Okay, not prepared. Postpone this exam for the next week, for the following week. For the following week, if you feel you're not prepared. And let's take a quick look. If I don't hear from you, if I don't hear from you, if I don't hear from you until the end of the day, I will assume that the exam will be the day after tomorrow. Okay, the exam will be the day after tomorrow. The exam will be the day after tomorrow. So from anyone? And let's take a look at the book. Oh yeah, no, before we take a look at the book, let's see what we covered, right? So far, I still didn't post the recordings for for the last class, right? I will post it today. Here you go. That's we were doing examples of uniform circular motion. First is the flat curve. Okay, this one is like an example for the flat curve. Oh, okay, and that's the material for the exam 2. And what they're going to do now is going to be an example of banked curves. We should have some material to go. So it doesn't look like we're going to be able, hopefully we'll be able to finish today. But let's see, you know what? Let me copy that. Copy that. And example 5. Okay, this other example is about negotiating a curve. Okay, let me, here you go. Negotiating a flat curve. And then there's also the other example that's negotiating a banked curve. It makes a huge difference when you bank a curve at the exit of the freeway. Many freeway exits have the banked curve. They are far safer than the exits that are not banked. Okay, so here you go. That's what have covered so far. Today we're gonna at least cover this one. Let's put it in italics. Okay, let us start covering banked curves. More students coming. Banked curves. Okay. Well, first you have to know what banked curves mean, right? First you have to know what banked curve. Am I sharing the screen with you folks? I believe I am, right? Just confirm that with me. Yes. Okay. Thank you. Okay. You saw the example of a flat curve. Here you go. Here's the example of a flat curve. Seeing it from sideways, right? Seeing from the top is something like that. Here's the car at this instant of time. Here's the other car at this instant of time. When we look at the car along the XYZ plane, along, right? The XYZ plane, the XY plane, right? Or into parallel, here's parallel to the XY plane, or into the XZ plane. That's how the car looks like in the regular curve. But then people discovered that some time ago that a banked curve is far safer than a flat curve. Of course, it's more expensive to build something like that, right? And that's what a banked curve is. It's a curve that's banked towards the center. That's it's tilted towards the center of this circle. It still looks like that. It still looks like that, right? But it's a plane that's tilted towards the center. It's like a section of a cone, right? Kind of a section of a cone. Okay. And that's that's a very interesting problem. Okay, consider, for instance, I'm going to give you just a qualitative idea of first, right? I will give you a qualitative idea of how the bank curve can be safer than the regular curves. Okay. And they use that in many racetracks, not just in the freeway exits, but in many racetracks. Let's take a look at some racetracks out there. Okay, Langley, let's see, Langley Speedway. Okay, when I used to work at NASA, we used to have this Langley Speedway in front of NASA, okay? I never went there. I lived 10 years there in that region, and I never managed to go and see this Langley Speedway that's located in the city of Hampton. right in front of NASA's gate. Let's see if they have a banked curve there. Doesn't look like they have a banked curve there. Yeah, they don't have a I don't. Doesn't look like they have a banked curve there. Okay. Oh, it looks like this one is banked here at this point. That looks like if it's a bank curve, is a very shallow one. Okay. And there's a racetrack in Belgium, Formula One, Belgian Grand Prix, in which they Formula One car racers they race in there, and that one it has a region that is a banked. Okay, let's see if we can get some pictures of that. Here you go. That's the racetrack. Let's see if they have a bank. They do have a banked curve, but I wonder if they use it. Oh, banked corner. See that? The old Spa-Francorchamps. Okay, that's the name of the speedway. Old Spa-Francorchamps. Spa was modified to make even faster, shortening it to 8.7 miles. All these low corners were taken out. The Stavelot hairpin was bypassed and made into a fast banked corner. Okay, so here you go, banked Stavelot corner. I wonder if they have a picture of that. So that's the name. Banked is some old pictures. Too bad they don't have a picture of the banked curve. Okay, so let's see. Let's put here in the internet. Banked Stavelot corner at Old Spa-Francorchamps. Let's see. Here you go.
We're now entering the Hollow corner. Hurrah! This fast kink is immediately followed by the Stavlo corner. Stavlo is a very slow corner, and it's based on an intersection. In front, you'll see the slow driver that bothered Herman following the pre-war track, which is leading to the original Stavlo corner.
Okay.
In 1947, this new banked Stavlo corner cut off the old one to make the circuit even faster. After Raidillon, this was the second artificial corner that was built for the old Spa-Francorchamps circuit. Just like Raidillon, the new Stavlo corner was a small permanent section in an otherwise normally street-based circuit. What's interesting, though, is that Raidillon is obviously now part of the permanent racetrack, whereas the banked Stavlo corner is now public road.
Well, I could hardly see any bank in there. So it looks like it's a very shallow bank as well. Okay, and but what banked curve means again? It means something that's tilted towards the center. And we can explain this safety features of those banked curves, but just by doing a force diagram. Okay, here you go. So assume, for instance, let's just first look into the situation in which you have an icy road, right, in the bank, or even oil spill in this curve, and the car is at rest. Okay, this this little exercise here is going to give you an idea of how the banked curve works, especially in terms of the force diagram that we're going to come up with, the free body diagram that we're going to come up with that, okay? So suppose that we have an icy road, no friction whatsoever, either an icy road or an oil spill here in the road, which is common, okay? Cars, they end up spilling oil in the road that will make it the track slippery. If the car is at rest at this banked curve, what's going to happen? It's going to slide towards the center, right? That's very, you can picture that, right? We slide towards the center if the road is icy and has no friction. Okay. However, if the car is going very fast, something else is going to happen through a patch of oil, for instance, or through a patch of icy, through a patch of icy road, right? The car will slide away from the center of the curve. Can you picture that? Right? No, just like we had in the previous example with the flat curve. Okay? However, there is, because we have those two extremes, right? At rest, the car would either slide down very fast, the car would either move away from the center. So that suggests, because you have those two extremes, okay? That suggests there must be a sweet spot speed, okay, in which the car will be able to safely negotiate this curve, okay? Anywhere between v equal to 0 and anywhere between v equal to 0 and v equal to very fast, okay? Anywhere between those two speeds. That give us a hint, right? That there will be a magical speed in which the car will be able to negotiate this banked curve safely, and where it's possible to calculate this speed, okay? So here you go. Suppose that we have an angle theta here. This curve is inclined by an angle theta. At just the right speed, the car will be able to negotiate the curve. And here's the radius of the curve. Okay? So I'm going to write that down in my notes. Banked curve. Banked curve, okay? A banked curve is a curve tilted towards its center. A banked curve is a curve. It is not, in other words, it is not a flat curve like before. Okay? Let us perform a thought experiment. Okay? One, consider a banked curve. Banked curve with an angle theta. Tilted, a banked curve tilted, right? With an angle theta towards its center. Two, consider, assume that there is an oil patch or a patch of icy road in this banked curve. Okay? Three, a car placed at this oil patch. Okay? Placed at this oil patch. A car that's at rest. A car that is at rest and placed at this oil patch will tend to slide towards the center of the curve, right? Just like you saw in that drawing. I'm just documenting what we mentioned before. Similarly, a car that is moving very fast when passing through this oil patch will tend to move away from the center of the curve, okay? And I'm going to illustrate what I mean by away, okay? The car is not gonna climb, no. It's gonna climb in a different way. It's gonna climb. I'm going to illustrate that for you. Here you go. I'm gonna use this illustration right in here. No, even better. I'm gonna use this illustration right in here. Okay. Here you go. Car at rest will slide towards the center of the curve. Right? Car moving very fast will slide away from the center of the curve. And by sliding away from the center of the curve, I mean the following. Here you go. If at a given instant of time the car is here, because there is no friction whatsoever, the car will move tangent to the path where it is at that instant of where it was at that initial instant of time, okay? That would be the path. It is moving away from the center of the curve, yes. It's moving away because the position vector is increasing in length. That's what I mean by moving away. Make sense? Okay. And don't forget this curve is banked, right? Banked toward the center. One more student coming in. And I'm going to put, that's the initial vector position. I'm going to put R naught here. And this other one is a final vector position, RF. That's what happens when you have an icy road, an oil patch. It happens both with the flat curve and the banked curve. Okay? So we have those two extremes, okay? So we have these two extremes for the car going through the oil patch at rest and moving very fast, or towards slides towards the center or away from the center respectively. Okay? 6. This suggests that there is a magical speed where at this value the car will be able to negotiate the curve safely, even if it is moving at this specific magical speed. Okay? That's what our thought experiment is suggesting to us. Is suggesting us. Okay. Okay, and let's see how we can get to the solution. Okay, so uh, oh, the first step is for you to come up with the forces, right? The free body diagram, apply it to your car. And, the force that's always there. Okay. If the car is going to go through the patch of oil, the first thing that we must have a centripetal acceleration there. Okay. A centripetal acceleration towards the center. Don't forget, the car must remain in a single plane. Okay. You cannot be varying the plane to safely negotiate this curve. So consequently, the centripetal acceleration must be in the horizontal direction, not in the vertical direction, not in this direction, okay? Not in this direction. It must be in the horizontal direction, the direction of a centripetal acceleration. And now let's take a look at the forces, right? That are being applied. The weight is always there. The weight of the car is always there. And of course, there will be a normal as well, okay? There will be a normal as well. Note that the normal has an inclination here because of the banked curve, right? Note that. The weight doesn't have an horizontal component because it's exactly in the vertical. But the normal will have an horizontal component that will serve as the centripetal force. Since there is no friction here between the tires of the car, there will be no frictional force to account for as part of the centripetal force. Okay? Let's see here. This one is something else. Okay. Car has just the right speed. It will be able to negotiate the curve. Here is the radius of the curve. Here are the forces, right? The weight and the normal. The weight, again, doesn't have any centripetal component, but the normal has. The normal has a centripetal component. And now, remember, it's not going to be the force of static friction that's going to be our centripetal force, but it's going to be the horizontal component of the normal that will serve as the centripetal force, okay? The vertical component of the normal is going to cancel out with the weight, and the horizontal, and the horizontal component of the normal will serve as the centripetal force. Nice enough? Can you picture that? Okay. I'm going to do another drawing here. Here we go. I'm going to come up with a vertical line here, not a vertical. Here we go. And I'm going to dash it as well. Okay. And this angle that you see right in here is going to be the same angle as this one. Okay. If this curve is flat, theta is 0. If this curve is banked, as I increase this angle here is going to be increased as well. Okay. And I can go ahead and state that this angle right in here, I'm going to put in a different color. Yeah. But let's increase that. Right in here. This angle is going to be the same as the other. Can you explain what the second line, red line is? Oh, the second red line here is just normal here. I just copy it from here to here. Okay, let me put that here. Okay, I'm going to put it here. Normal, right? And the weight. I just want those forces to be next to the centripetal acceleration. Okay, and not this one right here. That's how we usually do, right? When we want to say that angles are equal, angles equal to each other. Right in here. And now we can go ahead and write down our equations of motion. Okay, this suggests that there's a magical speed, right? Right? Where at this value, the car will be able to negotiate the curve safely at this specific magical speed. X7. Identify the forces, okay? Identify the forces acting in the car. Now, how to solve the problem? Here you go. How to solve this, right? One, identify the forces acting in the car. Two, illustrate the direction of the centripetal acceleration, which must be in the horizontal direction, right? Let's put this one as the first one to be consistent with the drawing, okay? Here you go. Illustrate the direction of the centripetal acceleration, which must be in the horizontal direction. Here you go, not parallel to the surface of the banked curve, okay? Otherwise, the car is not going to be in a single plane, but it's going to be in multiple planes, right? Because it will be sliding along the track towards the center. Identify the forces acting on the car, right? In the car. After identifying these forces, let's see, only the weight and the normal. There is no friction because of the oil patch on the surface of the curve. Okay? These forces, after identifying these forces, notice the following. The weight has only a vertical component. In other words, no horizontal component for the weight. Right? and but the normal has both a vertical and horizontal components. Has both vertical and horizontal components. Okay. For the vertical component must cancel the weight, and the horizontal component will be the centripetal component. Centripetal force, Let's see, the vertical component must cancel the weight, and the horizontal component will be the centripetal force. Will act, right? Not will be, but will act as the centripetal force being applied to the car, since it is parallel to the centripetal acceleration. Okay. So what we want to do, okay, so what we want to do the following. Let's put it here, example, right? Consider a curve, a banked curve of angle theta, right? Go. Here you go. Theta. There is an oil patch on the road, on this banked road. That reduces the friction to 0. Right? Find the magical speed that a car must have to safely negotiate this banked curve. Okay? Example. Solution. And then we have all those steps, right? Now it apply Newton's second law. And that's what we're going to do now. Like that. Net force right, must be equal to mass times acceleration. Let's not forget that this acceleration is a centripetal acceleration. Okay. Oh, I gotta put something else here, right? Consider a bank curve of angle theta, and there is one more important piece of information here, and radius r. Okay, that was missing here in this problem. Okay. We identified that there are only two forces, right? The weight and the normal. what we have here are two equations in the x and y direction. Okay, and this equation can be broken down. Let's see here. Into two components along the x. Right, you go. And y directions. Okay, here y direction. There are no, because the weight has no horizontal component, right? The weight has no horizontal component, so we can remove the Wx component of the weight vector there. What else? The centripetal acceleration has no vertical component. Okay, so here you go. So here you're gonna have 0, right? No vertical components for the centripetal acceleration. Write everything as a scalar equation. Okay. So we go. Going back to our drawing. One more student coming. The horizontal component of the normal is going to be sine of theta, normal sine of theta. Okay. Here's gonna be normal. Normal sine of theta. Okay, and the horizontal component of the acceleration can be written as v squared over r. The vertical, and let's not forget too, that because the normal is pointing to the left, it means that we have a negative sign here, right? But the same thing can be said about the horizontal component of the acceleration, right? The horizontal component of acceleration is pointing to the left. Consequently, we must also have a negative sign for this magnitude. Okay, here you go. This negative cancels this negative, right? This negative cancels this negative, and I'm gonna show it next time, in the next step. Okay, my y component of the weight is going to be minus mg in the y direction. My y component of the normal is going to be in the positive y direction, but instead of sine, it's going to be a cosine. Okay. Next, this negative sign cancel out this negative sign. Okay. Remember, we want to find this v here. We do not know what n is. but we do know what G is. We do know what R is. We do know what theta is. I'm going to highlight the parameters that we do not know. N, we do not know V. We do not know M either. See, we have 3 unknowns, but only 2 equations. You know, 3 unknowns, M, N, and V, but only 2 equations. At sight, you know, at first, it seems that we cannot solve this problem because we have more unknowns than equations. Okay? But let's see. But let us keep on solving this problem. You know? But don't give up. But don't give up. Let us keep on solving this problem to find out if it is solvable or not. Okay? So the next step would be to put this guy on the other side of the equation. When you put on the other side, we must change the sign, right? And if you pay attention, something magical is going to happen. Sometimes you get things like that in physics and math, okay? Even though there are 3 unknowns and only 2 equations, under certain circumstances, it's going to be possible to solve the problem under certain circumstances. Okay? And look what's going to happen. I found what n is. N is still given in terms of an unknown parameter, which is the mass. But hey, wait a minute. I'm going to substitute this guy right in here. And then what's going to happen to the mass here? This unknown parameter is going to be canceled out. Even though you do not know the mass, it doesn't matter if you know the mass or not. It's going to cancel out from your equation, and you will still be able to solve the problem. Okay? Isn't that nice? It happens with frequency in math and physics. Let me move downwards. Yeah, like that. Now I'm going to concentrate on this equation alone. I'm gonna copy the other one anyway, just for the sake of completion. M, see that? It's gonna cancel with M here. Sine theta over cosine of theta is going to become tangent of theta. Oops. And now we have our own problem almost solved. We find that the sweet spot, right? That magical speed capable of negotiating this icy road is going to be given by the square root. Strange. Okay, so what happened to my I need my square root here. Let's see. No. Wow, something. Okay, I have to click it here. That's why. Here you go. Okay, so that's going to be our speed, your magical speed. It's going to be depend on the angle of theta, the radius, and the acceleration of gravity. Okay. Let's take a look at the book. And hopefully we'll be able to come up with a Wiley plus 942. We have time. Here we go. Wiley resources. Launch. And centripetal force right in here. Let's see, banked curve is the next. Okay, here you go. A banked plane, okay? If you want to make a curve with an airplane, you have to bank it. But in this case, the role of the centripetal force is going to be the horizontal component of the left of the airplane, which is taking the role of the normal, okay? And banked curve. That's how it looks, a banked curve look like, okay? So if you extend this line to the center, right, you're going to see that this banked curve generates a section of a cone. Okay, and here you go. That's the same equation that I got, right? And now we have this example. The Daytona 500 is the major event of the NASCAR season. It's held in the Daytona International Speedway in Daytona. The turns in this oval track have a maximum radius of 316 and are banked at 31 degrees. Suppose this maximum radius turns were frictionless, right? At what speed would the cars have to travel around them? And that's very important, right? If some oil patch appears because of an accident, the drivers are told in advance, they can adjust their speed and go safely through the oil patch, right? So 31 degrees. And then you go ahead, put the numbers in there, 316 meters. The G is approximately 10 meters per second square. Tangent of 31 is whatever, right? And that's the type of speed you get, 96 miles per hour. So if you adjust your speed to 96 miles an hour, you'll be able to safely negotiate that frictionless path that's in the road. Okay? Check for a numerical example, right? For a numerical example, check example 9 in the book. Okay, note that we will not be able to find the normal force because it depends on the mass of the vehicle, right? We'll be able to find the speed, but not the normal force. Not the normal force. The problem can be partially solved, but not completely solved. In order to be completely solved, we must know what's the mass of the car. And that's the nice thing about a banked curve. Okay, and the banked curve becomes even safer if there is no oil patch in the surface. Okay, if there's no oil patch in the surfaces, then now you're going to have an additional force that's going to be the force of static friction. With this force of static friction, then you are going to end up having a range of speeds that you can use to negotiate this banked curve. Okay, there will be no need for the driver to turn the wheel. You can keep the wheel in the horizontal direction for either case. In the first case, for a frictionless surface, you keep the wheel in the horizontal direction, adjust the speed to that magical speed, and you'll be able to negotiate the curve. If there is friction in there, it's going to be even safer, because now instead of having a single speed value, you're going to have a range of speeds, because now your friction is helping you out negotiate this curve. Okay, and again, the driver will be able to keep the wheel horizontal. It doesn't have to turn the wheel. Any questions? I think it's a very nice, and that's the type of thing that you can experience with your bicycle too. Okay, there are some tracks out there that are banked, and you can take your bicycle to those tracks. University has those types, and most likely high schools too have this type of track. You can take your bike there to this track and observe to this banked track and observe. You're going to see that you won't need to turn the wheel of your bike. Okay, you just keep it straight, and because you have an horizontal component of the normal, the horizontal component of the normal is going to do the job for you. That's another example. That's another real life example. Illustrations right in here. Now let's go to the attendance roster right in here. Lecture 28. Let's see. Audrey, are you there, Audrey? Just send me a text message or talk through your.
I'm here.
Okay, thank you, Audrey. Another one is Matthew. I don't see Matthew here. Matthew disappeared, huh? Brianna, are you there, Brianna? Hello, Brianna. I don't hear from Brianna. She must be away from her computer. Jazzy, are you there? Thank you, Jazzy. Gabriel Contreras. I don't see Gabriel here. Liliana Cortez. I don't see Liliana. Juan Escalera. No Juan here. Molly. Molly's definitely here, right?
Here.
Okay, Henry Kim. Thank you, Henry. Ruth. I don't see Ruth here. Noemi Martinez. Hello, Noemi. I don't hear from Noemi. Let's see. Danae Miller.
I'm here.
Thank you. Ramon Olivares. I don't see Ramon either. Next is Taylor Form. No Taylor here. Stephanie Ramos.
I'm here.
Okay. Jeremiah Reyes. Thank you. Jeremiah Sean Rosario. Thank you. Ali Standard. Hello, Ali. Okay, it's not answering. Next is Jason Strait.
I'm here.
Thank you, Jason. Elena Trujillo. Elena. Another student that must be away from the computer. Let's see. More here. Jason Valadares.
Here.
Thank you, Jason. Stephen Vadhapali. Stephen's not here. Larell Williams. Larell is not here either. Nuhamin Monimu. Nuhamin not here. Alia Zavala. Thank you. And let's see. 9:52. 1, 2, 3, 4, 4, 15, 16. Okay. So, I'm gonna give another opportunity. Let's see, Brianna, are you there, Brianna? Another opportunity for those students who didn't answer. Let's see, Noemi, are you there? And Ali, standard. And Elena. Okay, so just a reminder, it's we're originally scheduled for an exam the day after tomorrow. Okay, chapters 3 and 4, labs 2 and 3, and we still have an opportunity to postpone this exam to the other week. Okay, I told you that at the beginning that if you want me to do that, let me know. Otherwise, if I don't hear from you, we are scheduled for. We have the exam scheduled for the day after tomorrow. Okay. 9:53 right now. And let's have a break. 9:54 a.m. to 10:09 a.m. Right? No questions? Okay, so I see you in the next 15 minutes. I'm back here. And we are done with the section on banked curves. Let's get the, okay, so here you go. And now we are going to look at satellites in circular orbit, which is also a type of uniform circular motion. Now, here you go. Satellites in circular orbits. And I am going to get the illustrations here for you. Oh, here you go. That's an illustration here from the book. We're gonna get our own illustration. Okay. Remember, this is Newton's third law of motion, right? And Newton's third law of motion also applies to the gravitational theory. And that's what we are looking at. The illustration that I want to show you is elsewhere. Okay, should be right in here. Okay. Should be right in here. Okay, so let's start with those right here. You want. Satellites in circular orbit. Circular orbits. Okay, and remember that you have to remember that other law of physics, the law of universal gravitation, and Brianna, right? So let's first give attendance to Brianna. Brianna Carrillo. Let's see. I'm gonna give you a opportunity for Noemi. Noemi, are you there? Noemi? Another opportunity for Ali Standard and Elena Trujillo.
Here.
Elena? Okay. Okay, thank you, Elena. Okay, so let's go back to the lecture, right? So recall that when we have two masses close to each other, right? Mass 1 and mass 2, they, at distance d, they exert a force on each other. Force of 1 due to 2. Okay. And force of 2 into due to 1. Or you can rename it force of 2. You can also, redefine, right? Like I had defined before. That's force of 2 in mass 1. Okay? Force of 2 in mass 1. It all depends how you define it, okay? I prefer to define it as force of 2 in mass 1, right? Force of 2 apply it to mass 1. I prefer this way. Force of 1 apply it to mass 2. That's what this notation means. And I don't need to keep, I can just, here, swap them around, right? All right, and that's the distance, the vector position from 1 to 2. That's the unit vector, remember that. And there is a formula for that. The recall that whenever you have you have two masses interacting with each other, they exert a gravitational force given by force equal an attractive. This is an attractive gravitational force given by M1, M2. We still have a big G here in front of. It's not the same as your small g, it's a different one. It's a universal constant. The small g is not a universal constant. The small g is the acceleration of gravity on the surface of the Earth, right? So don't confuse this big G with the small g. I'm going to emphasize it here. They're not the same thing. They're completely different beasts, right? Different. That's the one here. Difference of load, small g. Okay? Like that. And they, if you have a satellite orbiting a planet, and by the way, this force here, the above force allows, it's possible to prove that, it's possible to prove mathematically that the above force allows for uniform circular motion and other types of motion. Okay, and by other types I mean elliptical, not just circular, but elliptical, parabolic, and hyperbolic. It's possible to prove that, but we are going to be concentrated on the simplest one. However, we will concentrate on the simplest one, that is circular motion. Circular motion. And the situation goes like the following. Okay, so here's an illustration of the type of motion that satellites undergo around the Earth, and the type of motion that planets also undergo around the sun. Okay, this thing can be either the Earth and a satellite, or here can be the sun and a planet. Can be the planet Earth. The orbit is very close to a circular motion. Okay, because the force is a radial force. Notice that it's pointing towards the center of the Earth, which is located at the center of the circular trajectory, the circular orbit. Okay? Consequently, this type of motion can be studied in terms of uniform circular motion, can be modeled in terms of uniform circular motion. There's no other force being applied to this planet, to this satellite. Here's my force diagram, right? And we are concentrated only on the forces being applied to this small object, a satellite in orbit, the Earth. There's no other force being applied to it, just the gravitational force. And one thing that you might want to do, consider a satellite of mass. Consider a satellite. I'm not even going to tell us the mass of the satellite is, so we don't need that. Orbiting the Earth of mass, big M, okay? At a distance r from the center of the Earth. Okay, let's take a look at treat that as those as an example. Okay. From the center of the Earth. Find the satellite orbital speed. Okay. Another example using uniform circular motion. Let's see. Consider a satellite orbiting the Earth under uniform let's see, circular motion. The mass of the Earth is M, big M, and the satellite is at a distance r from the center of the Earth. Find the satellite orbital speed. Okay. And I'm going to put it here, solution. And I'm going to use exactly the same principles, the same idea that we have used before, okay? So here you go. Not only we have a force vector here, but we also have a velocity vector here. Okay, and I'm gonna put it with a different color. Like that. The velocity is tangent to this path. Here I put capital R, let's put lowercase r. We don't need to know necessarily the mass of the satellite, okay? Don't need to know its mass. And this problem is just what we have been doing before, okay? So there is the only force applied to the satellite is the gravitational force. Let's put this, the only force applied to the satellite is the gravitational force from the Earth, gravitational force from the Earth, okay? So here we go ahead and we write down our equations, lowercase m, uppercase m. We do not know what's lowercase m, but we are not going to need to know that G is given by any book, R is given by the problem, big M is also given by any book, okay? You can consult the mass of the Earth in any book, even in the internet. And because this is the only force applied to the Earth, then we can write down on the right side the mass times centripetal acceleration, like that. And the centripetal acceleration is going to be given by v squared over r. Do you remember that I told you that we do not need to know what m is? Right? Lowercase m is, we don't need to know it. Let's keep it here. And that's because this little m here is going to cancel out with this other little m here. It doesn't matter what's the mass of the satellite. They're all going to have the same orbital velocity if their radius are the same, okay? So let's keep on solving it. Let's keep on solving. What we should focus right now is going to be this equation right in here. We can simplify this equation by canceling out lowercase m and lowercase m. This r squared is going to cancel out with this other r right in here. P squared. And we are going to get a square root right in here when we solve this equation, v equal. So that's the solution. The solution. So we know big M, we know small r, we know big G is given by the problem. We do not know M, but we do not need to know it to solve this problem. Okay? That's we can now we can start to put numbers into this equation to find out, to have some idea of the type of order of magnitude that that we are dealing with. Okay, so now consider a satellite orbiting the Earth under uniform circular. Okay. Let R, let R be equal to 400 kilometers. Find the orbital speed of the satellite at this height. Okay. No, wait a minute. Let R be, no, it's not 400 kilometers. It's going to be, let the altitude of the satellite be, I'm going to put it H. The altitude of the satellite from the surface of the Earth, right? From mean sea level, okay? From the surface of the sea, right? From the surface of the sea, the surface of the sea. The surface of the sea is usually mentioned as mean sea level. Be 400 kilometers. Find the orbital speed of the satellite at this height. Find the numerical value of the orbital speed of satellite at this height. Okay. We are going to apply this equation here, but let's not forget that now this radius here that you see is actually the distance from the center of the Earth to the point where the satellite is. So we have to rewrite this R here. This lowercase r is going to be the radius of the Earth plus the height of the satellite. Okay? That's how we solve this problem. And then you plug in all the numerical values. Let's do that. Okay, I already know what's the numerical value of that. It's not difficult to memorize this value. It's around 8 kilometers per second. That's what we call the orbital speed. Okay, and we're going to get our roster here. And G has a value, right? The radius of the Earth is documented in any book. Here, the height of the satellite is going to be 400,000 meters, like that. The radius of the Earth, I'm gonna put it here in meters, always with the same, using the SI units. The radius of the Earth is going to be around 6,500 kilometers, which is 6,500,000 meters, okay? Around, I'm saying that around. We can go to the internet and find exactly what this value is. Radius of the Earth. 6,371, see that? 6,371. And big G, what's the value of big G? Format cell, number, use separators. 400,000 meters. Big G is approximately 6 times e to minus. Let's take a look here. This is the type of gravitational constant. Gravitational constant. Here we go. Value 6.6. 10 to minus 11. Ideally, we should be memorizing that to solve problems more quickly, right? But I don't require that you memorize those things. 6.67 times 10 to minus 11. 6.67 times 10 to minus 11. And what are the units? Oh, okay, I gotta put that in scientific format. Okay, and then I'm gonna put the units here as well. What are the units of this guy? Okay, it's Newton, meter square per kilogram square. Is that right? I'm doing by heart here. Go Newton meter square per kilogram square. Yeah, just like I said. And let's put here the font, superscript, superscript. And what do we want? Going back to our problem, right? We want this orbital speed. Okay? And the orbital speed is going to be in meters per second. And after getting it in meters per second, I'm going to display it in kilometers per second because it's easier to visualize, right? And I'm going to write down the equation. Square root, right? Square root of big G, big M, big R plus H. Big G. Oh, I still need the mass of the Earth. I didn't put it here. Big M, right? Divided by R plus H. And also the mass of the Earth is documented everywhere. This one, I believe, is going to be 6 times 10 to 24. I believe it's going to be something like that. Let's take a look. Scientific. Okay, let's see if that's the value. Not exactly 6. It's going to be gravitational constant mass of the Earth. Yeah, see 5.9. 5.972. It's approximately 6 times 10 to 24 kilograms. Yeah, that's what I put here. And now we can go ahead and do the math. Already did. See what I'm getting here, 7,687 meters per second, which is almost 8 kilometers per second. This divided by 1,000. That's the speed of an orbiting satellite. The higher it goes, the slower it travels. Okay. If let's take a look what would be the speed if the height is exactly at the surface of the Earth, right? You go instead of 400 kilometers, let's put 0 exactly at the surface of the Earth. It's going to be 7.92. Okay. At higher orbits, 1, 2, 3, 1,000 kilometers. Let's put that in format, in scientific format. Yeah, here you go. 1,000 kilometers or 1,000,000 meters. You're gonna decrease a little bit from 7.6 to 7.3. I want to put it in order of increasing height. Okay. You go. I'm even going to put another, but instead of displaying in meters, I display that in kilometers to make things simpler. And I'm going to put in regular numeric format. Okay, here you go. 400 kilometers, 1,000 kilometers. I will put a comma separator. I don't want the decimal places there. Okay, let's see, 2,000 kilometers, 1, 2, 3, right? Wait a minute. Yeah. 2 million kilometers. Here you go. 2 million kilometers. 2 million meters. 6.9. See that? And so on, right? 3,000 kilometers, 6.5. As the altitude increases, of the satellite increases, the speed decreases. You get the idea? Okay. So in order for a rocket to reach low Earth orbit, to reach Earth's orbit, this rocket must fly at this speed, which is very difficult to achieve. Okay. Not every object can achieve this speed so easily. That's why it's so difficult to go to fly in space, to orbit the Earth in space, and even to just to go into space and return. Okay? Here's the speed. Okay? Let's take a look at another example. We have a bunch of interesting examples using that. Here you go. Here's the speed of the satellite, right? The orbiting, that's the speed of the Hubble Space Telescope at 600 kilometers, 598 exactly. Let's put 600 kilometers here, just to see how it looks like. Shift cells down. Okay. Here it's gonna be 600,000. We're supposed to get exactly the same result that the book got. 7.57 kilometers per second. Let's see what that. If you got, you get, okay, 7.57, right? Kilometers per second, which is 16,000 miles per hour. It's a very fast. This speed is something like 20 times the speed of the sound. Like I said, it's very difficult. So it's very difficult to achieve this type of speed, okay? And I'm gonna put it Mach. In terms of the speed of the sound, this divided by 0.34, 23 times the speed of the sound. And as we fly higher and higher, this orbital speed goes lower and lower. Okay? But that's the type of speed that spacecraft, that rockets must reach to orbit the Earth. 22 times, 21, 16 times the speed of the sound, okay? An airline, they fly slightly less than one time, Mach 1, slightly less than that. It's slightly less, it's 20 times less than that, right? Another example, here you go. Physics of locating a black hole. Okay, the Hubble Space Telescope has detected the light being emitted from different regions of the galaxy MI87. The black circle identifies the center of the galaxy. From the characteristics of this light, astronomers have determined that the orbiting speed is this much speed, which is 700 kilometers per second, 750 kilometers per second, right? Or matter located at a distance from the center. Find the mass m of the object located at the galactic center, okay? So the idea here is, this type of problem, given another example, given the speed, the orbiting speed, and the distance from the center from the center of rotation, right? Find the mass of the object. Let an object be let an object in orbit of a larger mass, okay? Given its orbital speed, v, and its distance from the center of the larger object, find the mass of the larger object. That's what this example is all about. Example. And then we go for a solution. I'm gonna put here my equations just to help me out. Okay. So let's illustrate the situation. The situation is exactly this one here. We have this larger object, we know the radius, you know the velocity, right? Well, like that. Know the velocity. Should be lowercase v. Know the radius. Find the mass. Find the mass. That's what this problem is all about. We still have the same force. It's a central force. It's not sideways. It's exactly toward the center of the larger object. Okay. So here you go. We already solved our equation, right? We have V here. We have big G here. We have R. And we need to find this guy right here. Okay? So we're going to use the same equation, but now we're going to solve it for big M. It's no different, right? So it's going to be V squared here. We're going to pass big G and lowercase r to the left side. And we will solve for the mass of the central object. And by the way, those measurements here, the velocity of the object around this other massive object, there are ways of determining that through spectroscopy, okay? We haven't studied spectroscopy, but there are some spectroscopic measurements that we can make to determine this velocity here. This radius that you see right in here can be determined if you know the distance to the object. Okay? You make an angular measurement of the side of the orbit, and you know the distance to the object, and from those two measurements, you can find out what's going to be the radius, which is this radius that I'm talking about here. It's this radius here that I'm talking about, okay? And let's use the numbers in the book. Okay. Numeric value R. Find M for the following values. V equal to, what that, 750 kilometers per second, right? Go back to the book. 750 kilometers per second, yeah? And the distance is 5.7 times 10 to the 17. R and R, 5.7 times 10 to the 17 meters or kilometers. Let's take a look there. Yeah, meters. 5.7 times 10 to the 17. Get here. All I need is this equation right in here. I'm going to use my Excel spreadsheet as well. Given V meters per second, given R in meters, find M in kilograms. I already have my G here, so I do not have to rewrite it. We are talking about 751,2,3,000 meters per second, 5.7 e to 17, right? Let's confirm that. 5.7 times 10 to 17. Find M, and then we have to write down the equation. You can do that with your calculator, right? Or you can do that with Excel, but you have to write this formula right in here. RV squared over G, R V squared over G, that's right in here. And we get, that's the size of the object. That's the mass of the object. 4.81 times 10 to the 39. The mass of the Earth, where's the mass of the Earth? I don't have the mass of the Earth here. Oh yeah, the mass of the Earth is right in here. See that? This object here is 14 orders of magnitude larger, 14 orders of magnitude more massive. Okay, that's for the mass of the Earth. What about the mass of the Sun? Let's take a look at the mass of the Sun in kilograms. Let's compare the mass of this object to the mass of the Sun. Sun is capital S. And you can go in the internet to find out what's the mass of the Sun. Of the Sun. 10 to the 30. 2 times 10 to the 30. 2 times 10 to the 30. So this object here is 9 orders of magnitude more massive than the Sun. It's a huge object. We are talking about 1 billion times more massive than the Sun. More, 2 billion times more massive than the Sun. Here you go. Divide by that. See, 2.4 billion times. 2,400,000,000 times more the mass than the Sun. Which tell us that this object cannot be a regular star. It has to be something else. Okay, we do not know stars with this type of mass. And in order to be something else, this object has to be a black hole. A black hole that feeds on the surrounding matter until it reaches this larger size, okay? So that's the example in the book. That's 1051. Let's see if we have another interesting example here. Yeah, we have another interesting example here. That has practical applications, the orbital radius for synchronous satellites. Okay? And then you have to know what synchronous satellite is all about. Let's see if we have another example. Yeah, good. Orbital radius for a synchronous satellite is it's not synchronous exactly. We call it something else. We call it geosynchronous satellite. Orbital radius, find the orbital radius of a geosynchronous satellite. Okay? The orbital radius r, given the mass of the Earth, find the orbital radius of a geosynchronous satellite. And then we have to define what geosynchronous satellite is all about. What geosynchronous satellite is? A geosynchronous satellite. A geosynchronous satellite is a satellite. Is a satellite that orbits the Earth in a period of 24 hours. Okay, the Earth rotates about its axis in 24 hours. So a geosynchronous satellite is going to have an orbital period of 24 hours as well. And this type of satellite has very important practical implications, okay? A geosynchronous satellite will always be seen at the same spot in the sky. If you're here on Earth and you're looking at a geosynchronous satellite, that satellite is going to be exactly at the same spot all the time. 20 degrees height, right? And let's see, 180 degrees from the north, 90 degrees from the north, let's say, 90 degrees from the north. Always going to be at that spot in the sky. That's what a geosynchronous satellite is all about. Do you have a picture? Do you have a picture? And what are the consequences of having a satellite at the same spot in the sky? You know, you can have an antenna pointing to that spot in the sky, and the antenna doesn't have to keep on following the satellite that it orbits the Earth. Okay, you don't have, you're going to have a very simple antenna with no motors whatsoever to make the antenna move and track the satellite. Most satellites, they move in the sky, like the Earth, like the moon, right? The moon rises on the east and sets in the west. The sun too rises in the east and sets on the west. Okay, but then those geosynchronous satellites, they're going to be at a given distance that it will not never rise and set in your sky. In your sky. Okay, let's do that. There is a way to. Okay, we already have the equations here, but let's see. Let's do this from scratch, right? Let's start with this one here. Here you go. Gravitational force. I'm going to do that from scratch. Gravitational force is equal to mass times velocity squared over r. Okay. Force is mass times acceleration, right? That's the gravitational force. That's the mass times centripetal acceleration. Note, see that again, we do not need to know the mass of the satellite to solve this problem. But we need to know the mass of the central object. Mass, cancel out this mass, right? R squared, we already did that before, right? Cancel out with the other R. And then take a look at this V. This V here is related to the orbital period of the satellite. Have you thought about that? Okay, this V, because it's uniform circular motion, this V is going to be equal to, okay, 2 pi r divided by the orbital period of the satellite, because this is uniform circular motion. 2 pi r is the length of the circle, of the circumference, and t is the orbital period of the satellite, which you already know is 24 hours. Okay, so we can keep on solving this problem for pi square, r square, t square, right? And now we can get this thing like that. Let's see if we can. Let's see if we can do any. No, we cannot do any simplification, right? Nothing is going to cancel, but there is a minor simplification. That remember, we want to know the radius of the satellite, the orbital radius of the satellite given t, right? Given the mass of the Earth, find the orbital radius of the satellite. I'm going to highlight what we want to find out. We want to find out this one. We want to find out this one, right? Here is going to be r cubed, big M. I'm going to put r bold-faced. Okay. And t squared is going to go to the other side. 4 pi squared is going to go to the other side as well. $10.59. Very soon you're going to have our break. I just heard here from another student that she would like us to postpone the second exam. Okay, and very soon we're going to talk about that. Here you go. Like that. R cubed. And then we substitute the values. Here is going to be the cubic root. Okay, so here you go. Raised to the, oops, not that, like that. Right? Or in other way, you can also put it in a different way, right? Radical 3, radical, oh, that's okay. Here you go. Another way of writing the same thing. And now we can go ahead and crunch those numbers, right? T is going to be 24 hours. So let's crunch those numbers. I'm going to put it aside. Go to my spreadsheet. Let's see, ratio. I'm going to put it ratio here. And now T, that'll be in seconds. Let's put that in hours first. Right, 24 hours. T in seconds is going to be 24 times 3,600. Okay. And now we need to find R. Let's find that in meters first. Write down the equation. Big G, open parentheses. Big G is right in here. Big M is right in here. Wait a minute. Yeah, that's right. Big M is right in there. T squared has to be in seconds. It's gonna be right in here. Don't forget to raise it to the second power. Divide by 4 times pi. And then you gotta raise. Let me see if everything is okay here. Yeah, looks like everything is okay. Sometimes we make mistakes on those equations, okay? That's why we should always review it properly. 1/3 must be between parentheses, otherwise we don't get the right result. What I'm getting here is, let's put that in kilometers. Okay, format cell. number. I'm getting 61,949 kilometers. Let's see if that's what the book has. Right? 61. Now, there's something wrong here, right? So I did, let's see. Did I do something wrong here? Big G. Big G. Maybe there's something wrong with my formula. Let's take a look here. Big G, big M, which is G2, T square. T square is going to be, okay, V, column V must be squared, divided by 4. Oh, I forgot to square the pi. See that? I forgot to square the pi. Okay, now do you understand why sometimes you don't get the right answers? Right? I like Excel because we can hunt down where the mistake is. And now, hopefully, we got the right thing. Now it looks more like the answer, 42,000 kilometers. Okay, 42,000 kilometers. He's getting, yeah, he's getting 42,000 kilometers. But then he's subtracting, okay, what is he doing here? He's getting the height, right? What's the height h above the Earth's surface? So what I calculated here was not the height h. What I calculated here was the distance from the center of the Earth. And I'm going to emphasize it. What's going on here? Oh, yeah, okay. I'm going to emphasize here in my enunciate of the problem. Give me the mass of the find the orbital radius. Yeah, the orbital radius, the distance from the center of the Earth of a geosynchronous satellite. A geosynchronous satellite is a satellite that orbits the Earth in a period of 24 hours, okay? So here we go. I got again 42,298 kilometers. The book got 42,300 kilometers, right? And again, this result that you see here is in reality the height of the satellite. He's subtracting this distance from the radius of the Earth. Okay, that's what he's doing. And that's a very interesting type of satellite orbit, because you can, like I said, you can point your antenna to that spot in the sky and leave it there. You don't have to follow the satellite in the sky, right? And there are international regulations that allocate spots in the sky for specific satellites, okay, especially in this geosynchronous orbit. So there are agreements, there are agreements among nations to reserve certain spots in the sky for a given country, for a given company, right? For a given type of satellite, and so on. And let's go here, 1106. Let's go back to my notes here. Like I said, I'm willing to change the date of the exam. I have been asked by actually I have been asked by 2 students to change the date of the exam. We cannot, at this point in time, we can do that, okay? Because we still have time to do that. And I just want to make sure it's okay to everybody, okay? So here you go. See, we can postpone it, and then after the exam, we're going to have a holiday. 11:07 right now. Okay, so if you have any problems postponing doing the exam on the other Wednesday, let me know, okay? And but because now we have more time for the exam, what I am going to do, let's see here. Lab 5. I'm going to include another chapter here, okay? So here you go. Wednesday, that's gonna be an exam. 3, 4. Now, what about chapter 9 here? Okay, that's gonna be an exam, so we have to change this one. Chapter 9, let's see. Yeah, we almost finished chapter 5. Hopefully we'll be able to start chapter 6. Let's see, chapter 6 here. So let's include chapter 5, since we gain 1 week, right? For now, I'll leave just labs 2 and 3. And 6, work. Let's see, work 1, work 2, lab 4 do, and no, it shouldn't be chapter 9 here. Chapter 9 should be here. Chapter 9. Okay, and so the day after tomorrow, we are going to have a lab, a regular lab. I will send, I will post an announcement in Canvas advising everyone that the date of the exam has changed, okay? And 11:10 right now. Do you have any questions? Okay, so if you don't have any questions, let's have a break. 11:10 from 11:10 a.m. to 11:25 a.m. Okay. So I will see you in 15 minutes. Okay, so here you go. We are back here. Now let's take a look what we have done so far. Satellites in circular orbit. 1, 2, 3, 4, 5, right? 2 more to go. Let's see if we can finish today. Doesn't look like we will be able to start the next chapter, but it looks like we'll be able to finish this chapter today, okay? The next one in line here is apparent weight and apparent weightlessness and artificial gravity. Here you go. Next section is apparent weightlessness and artificial gravity. Okay. Well, by the same token, remember that chapter that we're looking, chapter 4, right? We're looking at chapter 4, in which I covered this material on apparent weight. Let me get that for you. Here you go, Newton's law of motion. Right here. And then I had that illustration, that color illustration that a friend of mine did for me. Okay, right in here. Okay, so here what we have the case of a, I don't want that here. Here you go. I don't want that. Good. We have the case of an elevator that is undergoing free fall. You cut the cable of the elevator, and the elevator is accelerating downwards at 10 meters per second square. Okay? When something like that happens, you're going to feel weightless inside this elevator. Okay? It happens that this type of situation happens not only in a one-dimensional motion, but also happens in two-dimensional motion. Okay? So, and we can prove that, especially when an object is undergoing circular orbit around the Earth, okay? And then we can prove that mathematically just by doing just by working on the Newton's law of motion, okay? So that's apparent weightlessness, okay? But the same token that you feel no, you feel weightlessness, right? Weightless in a inside a free falling elevator, you will also feel weightless while orbiting the Earth. Okay? And that can be explained rather easily by using Newton's second law of motion. Let me show how that is done. And I'm going to need some new drawings here. Going back to this one here. Okay. So now I'm going to zoom in. Suppose this one is your spacecraft, right? Suppose you're inside the International Space Station, okay, which is orbiting the Earth in a circular orbit. So we'll have to do the following. I'll have to do that from scratch, right? Because I do not have a picture for that. Sort of from scratch. Yeah, let's erase everything. Here you go. Erase everything. Just keep my grid lines. Good. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, like that. Now I have a circle. Okay, I'm going to draw your space station right in here. Here's the space station. I'm making a simple drawing of the space station here. And is orbiting the Earth. I'm going to fill, there's no fill at all, okay? That's your orbiting elevator. Think about that as your orbiting elevator, right? I'm gonna put it a little bit more to the left, and then I'm gonna do the following. I'm gonna do exactly what I did before. I'm gonna put a scale here inside this elevator, right? And I'm going to put my test subject on the top of this scale. Okay? Don't forget that I'll get that here. My elevator has an orbital speed, right? Here you go. Here's the elevator. I don't like this way. Let's get that like we had it before. test subject. Yeah, better. My vector velocity is going to be in a different color, okay? Just like I had it before. Velocity vector right in here. One more student coming in. And this center is orbiting the center right in here. Let me put a little mass here. The drawing is out of scale, okay? The elevator is not larger than the Earth, of course. And then you have to come up with the forces, right? You know, force diagram. Here's the weight. The weight being applied to our test subject. And of course, we must also have a normal force, which we still do not know what is the value of this normal force. Okay, and like that. I'm gonna put a different color. Normal force. Color-coded normal force. Okay. And of course, we have an centripetal acceleration. Here you go. Centripetal acceleration here. Yeah, I don't need to rewrite it from scratch, right? Green. Like that. So we got everything that we need. Okay. The weight is towards the center of the planet, so we can assume that the normal is away, but it can also be on the other direction, okay? What we are going to find out, we are going to find out the value of the normal. Remember, I told you that? The normal is whatever your scale indicates. Okay, here you go. That's the scale, okay? And that's the test subject. And then you're gonna be something like, it's gonna be something like that. The situation is like that. Here you go. Example, right? Treat that as an example. Consider an elevator, okay? Orbiting the Earth. This elevator is equipped with a scale that measures the mass of a test subject, that is inside the elevator. I call this elevator orbital elevator. Okay. Find the apparent weight of our test subject, Okay. So that's the That's how we formulate the problem. Like that, solution. Solution. Okay. You know, the following forces are being applied to our test subject. The weight, which is always there, and maybe the normal force. You're going to understand why I put maybe the normal force, right? The elevator is orbiting the Earth at the orbital speed. Let's see, consider an elevator orbiting the Earth at distance r from its center, okay? I have to put that to its center. From the center, orbiting at distance r from the center of the Earth. This elevator is equipped with a scale that measures not the mass, but the force, right? The force that a test subject measures a force, measures the normal force. Here you go. The normal force applied to a test subject that's inside the elevator, right? Distance r from the center of the Earth. The following forces are being applied to our test subject. The weight, which is always there, and maybe the normal force. The elevator is orbiting the Earth at its orbital speed. Okay? So here you go, just like before, we are going to have that Newton's second law, right? Let me copy that. Here you go. Net force. Okay. Net force is equal to the weight plus normal times mass times acceleration, equal to mass times acceleration. The acceleration in this case is going to be the centripetal acceleration. Putting everything in the radial direction, okay, we can come up with this simpler formula. I do not know if the normal is upwards or downwards, right? But I do know that the centripetal acceleration is in the same direction as the weight. So I can write like that. Okay? And now don't forget that the centripetal acceleration is, again, v squared over r, right? V squared over r. Here you go. And v, we already calculated v. We already calculated the orbital speed of an orbiting spacecraft, which is also going to be applied to our elevator, right? Let's see what it is. The orbital velocity is given by this equation right in here. This equation right in here. The orbital velocity squared from the previous example, okay? from our previous example, v squared is equal okay. But we also know, so let's go. So let's plug this v squared right in here in our equation. We're gonna plug it right in here. Let's see, I'm gonna do like that. Okay, and then I'm gonna repeat that and insert it here. Okay, let's go. Oh, what we get here? We get r squared, right? And guess what? We are almost done here. You might not notice it, but we are almost done. You know, the weight, what's the weight? The weight by definition, okay? The weight by definition is the gravitational force that's being applied to on our test subject, right? Remember that's the weight is all about. In other words, the weight is going to be given by big G, mass of the Earth, mass of our test subject, divided by the distance from the center of the Earth, the square. Okay? And now all you have to do is to substitute this right here in this equation. And I'm going to repeat that first. Yeah? Okay? I'm going to repeat that. Even better, I'm going to do like that. Here you go. And now I'm going to copy and paste the W right here. And the next thing that you have to do, you have to compare this term here with this other term here, which are they're exactly the same. Okay? And let's just compute here. They're exactly the same. This note that this term here is exactly the same as this one. And then what's going to happen? Since the term in the left is exactly equal to the term on the right, okay? This term on the left is going to cancel out the term on the right. And what does it mean? It means that the scale is exerting a zero force on the test subject. Okay? The above result states that the normal force applied by the scale on our test subject is zero. In other words, the test subject is subject to apparent weightlessness, right? Weightlessness, like that. Okay? So I have proved to you that if you're orbiting the Earth, you're going to feel weightless. Unless, you do something else, right? And unless you do something else, which is the next thing that we are going to cover. Here you go. Artificial gravity. Now we can talk about artificial gravity. as solution to the weightlessness apparent to the apparent weightless to apparent to the problems of apparent weightlessness. Okay. So now we have going back to our drawing board, right? So now my test subject is floating there inside, right? So the question is, how can we generate artificial gravity inside this elevator here? What can we do to ensure that those test subjects will be able to walk upright, just like they do on Earth? Okay. Well, the way to do that is to generate artificial gravity. Okay, and the way you do that is by, I'm gonna take advantage. Here you go. Now this guy here. Now I'm gonna erase. Let's see. I'm gonna do like that. Here you go. I'm gonna put my scale right in here. Suppose that you have a big cylindrical space station, okay? A big cylindrical space station, okay? And you want the inhabitants of this space station to walk freely, just like they would do on the Earth's surface, in the inner surface of the cylindrical space station. Another way of doing that is to place a scale on this inner surface of the space station and put our test subject on the top of the scale and ensure that the normal force here that we are going to have is going to be equal to the regular weight of our test subject, mg, okay? So here you go. In this specific case, okay, the cylindrical space station has an angular velocity, which is translated in terms of a linear velocity here at the edge, right? What else? We're going to have a normal force applied to our test subject. And there is no massive object around it, okay? Around this. There will be a centripetal acceleration. And we want this normal force here to be equal to the mg, where g is 10 meters per second square. Okay? And that is right, let's see, physics of apparent weightlessness. Okay, and the physics of artificial gravity right in here. Okay. So what we end up having here, okay, the only force acting in our test subject is going to be the normal force, because it's far away from the Earth, you know. And let me just state that in the problem, right? Artificial gravity, the solution to the problems of apparent weightlessness, and with example. You go. Consider a cylindrical space station that is far away from the Earth, from Earth. In this case, the gravitational force of the Earth can be neglected, far away from any massive object, be it the Earth or the Sun, okay? The Sun, the Earth, the Sun, or any other planet, okay? This cylindrical space station is put to rotate about its own axis. What should be its angular velocity if it were to generate an artificial gravity? An artificial gravity equal to G 9.8 meters per second square, okay? Like that. That's how we should formulate the problem. Let's see. Oh, there's more. I forget. Consider a cylindrical space station of radius r, that is far away from any massive object. The cylindrical space station is put to rotate about its own axis. What should be its angular velocity if it were to generate an artificial gravity equal to the one, okay, on the surface of the Earth, to the one on the surface of the Earth, right? Where G is 9.8 meters per second square, okay? Okay, since the space station is far away from any massive object, there is no gravitational force applied to our test subject, okay? And the only force that will be applied to him, her, is going to be the normal force. Okay? So we have the following equation here to deal with. Net force equal to mass times acceleration, right? And the only force that's being applied to the test subject is going to be the normal force. And this acceleration is going to be the centripetal acceleration. Centripetal acceleration. We want the normal force to be exactly equal to mg. We're running out of time, 2 more minutes to go. And the centripetal force, centripetal acceleration, is going to be what? V squared over r. Okay, where r is the radius of the cylindrical. Let's see, what should be, not the angular velocity, but what would be its linear velocity? Is easier problem. Linear velocity. Its linear velocity if it were to generate artificial gravity. What would be its linear velocity at its edge, right? At its edge, if you were to generate artificial gravity. Like that. 2 more minutes to go. Let's copy that and paste. The equation that we are interested now is going to be mg and mv squared over r. We want to find out this linear velocity. So I'm going to highlighted. I didn't say what is the mass of my test subject, but I don't need to know what the mass of the test subject because it's going to cancel out. Whatever is, remember, whatever it is, bold-faced are unknown variables. Okay, and M cancel out M. We solve for V square GR. Okay, and then we get square root right in here. V GR. Okay. Is that what the book has? Let's take a look. Square root of RG or GR. Okay. And if the space station is 1 kilometer, 0.7, radius, it will have to rotate the speed at the edge of the space station is going to be 130 meters per second to generate artificial gravity. Okay. So I think we're done with that. I don't want to do vertical circular motion because it's more. I decided not to do that. So we can. Maybe later on we have time to do that. Okay, so we're done with, for now, we're done with chapter 5. And we will skip 5.7 for now. 5.7 for now. 5.7 for now, okay? We're done with chapter 5. Any questions? Let's see, there's a question here. Thank you. Okay, you're welcome. So I see you again on Wednesday, right? I have office hours right now if you want to hang around. If you don't, I'll see you on Wednesday.
Thank you, Professor.
Welcome.